There's a moment that nobody can quite pinpoint, but everyone agrees changed everything. A moment somewhere around 3.3 million years ago when a hominin, standing on the shores of Lake Turkana in what we now call Kenya, picked up a rock and deliberately struck it against another rock. Not randomly, not accidentally, but with purpose, with intent, with the understanding that breaking one rock could create something useful, something that didn't exist before. That single action, repeated across thousands of generations, separated our lineage from every other creature that had ever lived. Because here's what most people don't realize about tools. They're not just objects. They're frozen thoughts. They're ideas made solid. Every stone tool ever created began as an abstraction, a vision of what could be, held in a mind sophisticated enough to imagine a future different from the present. Think about that for a second. Before you can make a tool, you have to be able to imagine it. You have to look at a rock and see not what it is, but what it could become. You have to understand cause and effect. Strike here, at this angle, with this much force, and a flake will detach. That flake will have a sharp edge. That sharp edge can cut through hide, scrape meat from bone, slice through plant fibers. None of this is obvious. None of this is instinctive. This is problem solving. This is planning. This is thinking. The earliest stone tools we found were discovered at a site called Lomekwi 3 along the western shore of Lake Turkana. They're crude by later standards. Simple cores with a few flakes knocked off, hammerstones worn from repeated impacts, but they're unmistakably intentional. The rocks didn't break this way naturally. Someone chose these stones. Someone struck them deliberately. Someone 3.3 million years ago was thinking, planning, creating. And here's what makes this discovery so profound. These tools predate the earliest known members of the genus Homo by about 700,000 years, which means our direct ancestors, the ones we think of as the first humans, didn't invent toolmaking. They inherited it, from Australopithecus maybe, or from some other hominin species whose name we haven't learned yet because we haven't found enough of their bones to classify them properly. Picture the landscape where this happened. East Africa, 3 million years ago. The climate is changing. Forests are shrinking. Grasslands are expanding. The Rift Valley is tearing the continent apart, creating dramatic geological features, volcanic activity, seasonal floods that deposit sediment in perfect layers, layer upon layer, preserving moments in time that we can read millions of years later, like pages in a book. The hominins living here weren't like modern humans. They were smaller, maybe 4 feet tall. Their brains were roughly the size of a chimpanzee's, around 450 cubic centimeters. They still spent significant time in trees, their long arms and curved fingers adapted for climbing. Hands with opposable thumbs, hands with the dexterity to grasp, to manipulate, to create. But possessing hands doesn't automatically mean using tools. Chimpanzees have hands, gorillas have hands, orangutans have remarkably dexterous hands. And yes, they use simple tools occasionally. Chimps will use sticks to fish for termites, rocks to crack nuts, but that's the ceiling of their technological achievement. Our ancestors did something different. They didn't just use rocks, they modified them, and that modification required a cognitive leap that we're still trying to fully understand. Here's how it probably worked. A hominin finds a rock with natural sharp edges, maybe created when it split during a freeze-thaw cycle or when it tumbled down a cliff. They use it to cut through something tough, animal hide perhaps, or thick plant stems. It works. The sharp edge is useful. Then the edge dulls. The rock is no longer useful. Now comes the critical moment. Does the hominin discard the rock and search for another naturally sharp one? That's what a smart animal would do. That's the chimpanzee solution. But one of our ancestors did something unprecedented. They looked at the dull rock and thought, I can make it sharp again. They remembered how the edge looked when it was useful. They imagined that edge recreated, and they figured out that striking the rock in a specific way could achieve that imagined result. This is called flink napping, and it's harder than it sounds. The rock has to be the right type. Not all rocks fracture predictably. Flint, chert, obsidian, fine-grained volcanic rocks, these work well because they have what's called conchoidal fracture. They break in smooth, curved patterns that create sharp edges. But sedimentary rocks like sandstone or limestone just crumble. Strike them, and you get dust and fragments, not useful flakes. So the first toolmakers had to learn geology, not consciously, not with formal understanding, but practically. They had to develop an eye for the right kind of rock. They had to test materials, remember which ones worked, seek them out deliberately. Tool-making sites are often located near specific geological formations where good stone could be found, and analysis of stone tools shows that early hominins would sometimes carry preferred stones for kilometers, rather than using whatever was locally available. This indicates planning, forward thinking, the understanding that I'll need this later, so I should carry it with me now, even though it's heavy, even though it requires effort. That's not animal behavior. That's human behavior, emerging 3 million years ago in creatures whose brains were 1/3 the size of ours. The Lemekwi tools are what archaeologists call Oldowan technology, named after Olduvai Gorge in Tanzania, where similar tools were first systematically studied. Oldowan tools are simple, core and flake tools created by direct percussion. You hold one rock, the core, in one hand. You strike it with another rock, the hammerstone, with the other hand. If you do it right, a sharp flake detaches from the core. Both the flake and the core can be used as tools. The flake has a sharp cutting edge. The core, with multiple flakes removed, becomes a chopper. This technology persisted for over 1 million years, from about 2.6 million years ago to around 1.7 million years ago. That's longer than our species, Homo sapiens, has existed. Think about that. The same basic tool design, essentially unchanged, for 1 million years. Not because the users were stupid, but because the tools worked. They solved the problems our ancestors faced. Why change what works? But here's what fascinates archaeologists. Even within the Oldowan tradition, there's variation. Some tools are cruder, with just a few flakes removed. Others show more refinement, multiple strikes from different angles, creating sharper, more consistent edges. This variation might represent different skill levels. Experts versus beginners. Or it might represent different purposes. Quick and dirty tools for immediate use versus carefully crafted implements meant to last. And this is where it gets interesting, because variation implies choice. Choice implies thought. If every Oldowan tool were identical, you could argue they were made by rote, by instinct, by mindless copying. But they're not identical. They show judgment calls. This rock is good enough. This edge needs more work. This angle is better than that one. There's also evidence of learning. Experiments where modern researchers try to create Oldowan tools show it's not intuitive. It requires instruction or extensive trial and error. Hit the rock wrong and nothing happens, or the core shatters uselessly. Which means the first toolmakers had to teach each other, or at least tolerate novices watching experts, learning by observation. This is culture, the transmission of learned behaviors across individuals and generations. Some chimp groups have different termite fishing techniques. But human culture is different in scale and complexity. And it starts here, 3 million years ago, with hominins teaching each other how to hit rocks together in specific ways. The hands themselves tell part of the story. Fossil evidence shows that hominin hands were evolving to be better suited for precision gripping. The thumb was getting longer relative to the fingers. The fingertips were developing more sensitive nerve endings. The muscles controlling fine motor movements were getting more refined. Evolution was shaping hands specifically for tool use, which means tool use was providing enough survival advantage that individuals with better hands were more likely to survive and reproduce. Why? What survival advantage did stone tools provide that was worth the evolutionary investment? The answer is food. Specifically, access to food that was otherwise unavailable or difficult to obtain. Stone tools let our ancestors butcher animal carcasses more efficiently. Whether they were hunting or scavenging, once they had access to a dead animal, sharp stone flakes could slice through tough hide that fingers and teeth couldn't penetrate. They could separate meat from bone, extract marrow, process the carcass before predators arrived or before it spoiled. Cut marks on animal bones from 3.4 million years ago, found in Ethiopia, prove that hominins were processing animal carcasses with stone tools, not just eating meat, which many primates do opportunistically, but systematically accessing it with technology. This is huge. Meat is calorie-dense. It's rich in proteins and fats that plant foods can't match. A diet that includes significant meat provides energy that can fuel larger brains, support longer pregnancies, enable faster growth. But obtaining meat is hard. Hunting is dangerous. Scavenging requires competing with specialized carnivores who are faster, stronger, better armed with natural weapons. Stone tools leveled the playing field. A hominin with a sharp stone flake could defend a carcass from a jackal or hyena, could cut off a portion quickly and retreat to safety, could process the kill efficiently before competitors arrived. This created a feedback loop. Better tools led to more meat. More meat provided energy for larger brains. Larger brains enabled better toolmaking. Better tools led to more meat. Round and round, over hundreds of thousands of years, each improvement building on the last. And somewhere in this process, something shifted in the hominin mind. Tools stopped being just expedient solutions to immediate problems. They became objects that could be improved, refined, perfected, objects that could be made in advance of need, objects that could be carried to where they might be useful, objects that represented investment, planning, foresight. At Lomekwi, at Olduvai, at dozens of other sites across East Africa, we find evidence of this shift. Collections of tools suggesting workshops, places where hominins came repeatedly to make tools from locally available stone, transport of preferred stones over long distances, stockpiling of useful flakes. All behaviors that indicate these weren't animals reacting to their environment. These were minds imagining, planning, creating. The very first toolmaker, that individual 3.3 million years ago striking one rock against another, probably didn't know they were doing anything revolutionary. They were solving a problem. They needed a sharp edge. They figured out how to create one. But that solution, passed down and refined over countless generations, set humanity on a path that would lead to everything we've become. From stone flakes to smartphones, from hammerstones to skyscrapers. If you're listening to this at night, trying to fall asleep, perfect. That's exactly why these stories exist. London at 3 a.m., somewhere in between. We're all here together, thinking about the deep past, about the moments that made us human. Because that's what the first tools represent. Not just technology, but humanity itself, emerging. The capacity to imagine what doesn't exist. The ability to make the imagined real. The drive to improve, to refine, to pass knowledge to the next generation. 3 million years ago, on the shores of an African lake, someone who looked nothing like us, but thought in ways we'd recognize as familiar, picked up a rock and changed everything. And in becoming a maker, they started us on the path to becoming human. Stand up right now. Go ahead, if you're not already standing. Feel your weight settling into your feet, your spine stacking vertebra upon vertebra, your head balanced at the top like a crown. This feels normal, natural, effortless. But what you're doing right now is actually one of the strangest things any mammal has ever done. You're balancing your entire body on two narrow points of contact with the ground. You're using an absurd amount of muscular energy just to stay vertical. And you're doing it all day, every day, without thinking about it. This is bipedalism. And it's one of the most important evolutionary innovations in human history. Perhaps the most important, because it came first, before big brains, before language, before complex tools. Our ancestors were walking upright millions of years before they were thinking thoughts we'd recognize as human. And that transition, from 4 legs to 2, changed absolutely everything about what it meant to be a hominin. The fossil evidence for bipedalism goes back further than stone tools. Around 6 to 7 million years ago, right at the point where our lineage split from the ancestors of chimpanzees, something started happening to hominin anatomy. The bones started changing in ways that only make sense if these creatures were spending significant time walking upright. Look at the pelvis. In a quadrupedal ape like a chimp, the pelvis is long and narrow, perfect for supporting a spine that runs horizontally. But in early hominins, The pelvis became shorter and broader, bowl-shaped. This provides better support for organs when the spine is vertical. It changes the attachment points for leg muscles, making bipedal walking more efficient. It's a fundamental redesign of the skeletal architecture. The spine tells the same story. Chimps have a C-shaped spine, one gentle curve from head to hips, perfect for a horizontal body plan. Humans have an S-shaped spine, curves that stack and balance, creating shock absorption and stability when standing upright. Early hominin fossils show this S-curve developing, the lumbar region curving inward, the thoracic region curving outward, creating the characteristic human profile. The legs changed too. They got longer relative to the arms. The femur, the thigh bone, developed an angle where it meets the knee, angling inward so that the knees nearly touch when standing. This puts the center of gravity directly over the feet, making balance easier. The foot itself underwent dramatic modification. The big toe, which in apes can grasp like a thumb, straightened and moved in line with the other toes. The arch developed, creating a spring mechanism that stores and releases energy with each step. The heel bone enlarged, providing a stable platform for weight bearing. All of these changes are visible in the fossil record. Australopithecus afarensis, the species that includes the famous fossil Lucy, lived around 3 to 4 million years ago and was definitely bipedal. We know this not just from skeletal anatomy, but from footprints. At Latoli in Tanzania, preserved in volcanic ash 3.6 million years old, there are footprints of 3 individuals walking across the landscape. The prints show a human-like gait, heel strike first, then rolling onto the ball of the foot, pushing off with the toes. These weren't apes occasionally standing upright. These were creatures who walked on 2 legs as their primary mode of locomotion. But why? What evolutionary pressure was strong enough to drive such a radical reorganization of the body? This question has obsessed paleoanthropologists for decades, and the honest answer is, we still don't know for certain. But we have some compelling theories, and probably the truth involves multiple factors working together. The most popular explanation is environmental change. Between 10 and 5 million years ago, Africa's climate was shifting. Global temperatures were dropping. Forests were fragmenting and shrinking. Grasslands and savannas were expanding. For apes who had evolved in dense forest environments, this was a crisis. The continuous tree canopy was disappearing, replaced by open woodlands and grasslands with scattered trees. In this new environment, moving between food sources meant traveling across open ground. And here's where bipedalism provides a clear advantage. Walking upright is more energy efficient than knuckle walking, especially over long distances. Studies comparing the metabolic cost of locomotion show that bipedal humans use about 75% less energy than quadrupedal chimps when walking the same distance. This efficiency matters when you're covering more ground to find food. In a forest, food is everywhere, above you in the canopy, around you in the understory. You don't travel far between meals, but in open savanna, resources are more scattered. You might need to walk several kilometers between fruiting trees or water sources. The hominin who could walk those distances more efficiently, burning fewer calories, had a survival advantage. But there's more to the story. Bipedalism also changes your relationship with the sun. This is something most people never consider, but it's actually crucial. When you're quadrupedal, your entire back is exposed to direct overhead sunlight during the hottest part of the day. That's a huge surface area, absorbing solar radiation. But when you stand upright, only your head and shoulders are exposed to overhead sun. Everything else is shaded by your own body. This reduces the total heat load by about 60%. In the hot African savanna, this matters enormously. Overheating is a serious threat. Most large mammals in hot environments are crepuscular, active during dawn and dusk when it's cooler, resting during midday heat. But bipedal hominins could potentially remain active during midday hours when other animals were sheltering. Less competition for resources, more time to forage, to hunt, to cover territory. The cooling advantage is even greater when combined with another uniquely human trait we'll explore in detail later. Humans lost most of their body hair and evolved the ability to sweat profusely. Bipedalism and hairlessness work together synergistically for heat management. Stand upright to reduce sun exposure. Lose the hair so sweat can evaporate efficiently. Suddenly, you're a creature that can walk for hours under the blazing sun while other mammals are panting in the shade. But bipedalism did something even more important than making walking efficient and cooling effective. It freed the hands. And free hands changed everything. Think about a chimp for a moment. When it's moving, knuckle walking from place to place, its hands are occupied with locomotion. It can't carry things while traveling, not easily. It might clutch a fruit in one hand while three-legging it awkwardly, but it's not efficient. For a quadrupedal ape, hands are part-time tools, available for manipulation only when the animal is stationary. But a bipedal hominin's hands are free all the time. While walking, while running, while standing and scanning the horizon. This means you can carry things. Tools, weapons, food, infants. You can gather more than you can immediately eat and transport it back to a safe location. You can pick up a useful rock and carry it for hours until you need it. You can hold your baby against your chest with one arm while using the other hand for balance or gathering. This ability to carry things is transformative. It enables planning in a whole new way. Instead of eating food where you find it, you can collect it and bring it to a central location. This allows food sharing, which strengthens social bonds. It allows division of labor. Some individuals can focus on gathering plant foods, while others focus on acquiring meat. Then everyone shares at the end of the day. Carrying tools is even more significant. Before bipedalism, tool use would have been limited to opportunistic situations. Find a rock, use it immediately for a specific task, discard it, but with free hands, you can make a tool and carry it with you, ready for when you need it. You can transport good toolmaking stone from where you found it to where you'll use it. This is exactly what the archaeological record shows. Stone tools found kilometers away from any source of that particular stone type. Clear evidence of transport. Clear evidence of planning. Free hands also allowed our ancestors to become better fighters and hunters. A bipedal hominin can throw objects with power and accuracy that's impossible for a quadrupedal ape. Throwing requires rotational torque through the spine and shoulders, a stable base for the wind-up, and precise timing for the release. The upright posture and spinal curvature of bipedalism makes all of this possible. Our ancestors became throwing specialists. Rocks, spears, anything that could be hurled at a predator or prey. This is a ranged weapon capability that no other primate possesses. A chimp can throw, but poorly, with little force or accuracy. A human can throw a rock or spear, hard enough to kill or injure from tens of meters away. This changes the dynamics of predator defense and hunting completely. But bipedalism came with costs too. Significant costs that we're still paying today. Walking upright puts enormous stress on the spine, particularly the lower back. The lumbar vertebrae bear the weight of the entire upper body, and the loads are asymmetric, varying with movement and posture. This is why back pain is so common in humans. We're paying the price for standing upright. Childbirth became dramatically more difficult. The biomechanical requirements of bipedalism meant the pelvis had to be relatively narrow to allow efficient leg movement. But the evolutionary pressure for larger brains meant babies' heads were getting bigger. Something had to give. The solution was to give birth earlier in development, when the baby's head is still small enough to fit through the birth canal. This is why human infants are so helpless compared to other primates. They're essentially born premature, unable to cling to their mothers, unable to move independently for months. This creates a dependency loop that reinforces social bonding and cooperation. A human mother with a helpless infant needs support from others. Food sharing, childcare assistance, protection. Human babies' helplessness is a vulnerability that drives social cohesion. Bipedalism also made our ancestors more visible. In a forest, a quadrupedal ape moving through the understory is relatively concealed, but an upright hominin walking across open savanna is highly visible. They can see further, yes, but they can also be seen from further away. This increased visibility to predators. Early hominins would have been prey animals for big cats, hyenas, crocodiles. Standing upright made them easier to spot. The solution was social behavior. Groups provided safety. Multiple eyes scanning for danger. Cooperative defense. The ability to throw rocks in coordinated volleys. Predators that might easily take down a solitary individual would think twice about attacking a group of alert, armed hominins. So bipedalism wasn't just a change in how our ancestors moved. It was a catalyst for social evolution, cognitive evolution, technological evolution. Everything cascaded from this one fundamental shift in body plan. And here's something remarkable. The transition to bipedalism happened relatively early in hominin evolution, millions of years before the dramatic brain expansion that we think of as the hallmark of humanity. Australopithecus was fully bipedal, with a brain barely larger than a chimp's. This sequencing is important because it suggests that bipedalism created the conditions that made brain expansion possible. Free hands enabled better tool use. Better tool use enabled better food acquisition. Better food, especially meat, provided calories for larger brains. Larger brains enabled even better tools and strategies. The feedback loop spirals upward. But in those early millions of years, our ancestors were strange chimeric creatures. Bodies built for walking like humans. Brains thinking like apes. Arms still long and curved, indicating they spent significant time in trees despite being primarily terrestrial. Feet adapted for bipedal walking, but with some residual grasping ability. They were in transition. Not quite ape, not quite human. Something new, something unprecedented, walking across the changing African landscape on two legs, hands free to carry tools and babies, eyes scanning the horizon for threats and opportunities. They didn't know they were pioneering a new way of being. They were just trying to survive in an environment that no longer quite matched the adaptations they'd inherited from forest-dwelling ancestors, but survive they did. Every culture, every language, every technology, all of it built on the foundation of walking upright. We carry that inheritance in our spines, in our feet, in our hands. The aches in our lower backs are echoes of an evolutionary compromise made millions of years ago. The vulnerability of our infants is the price we paid for standing tall, and it was worth it. Because standing upright freed our hands to reshape the world, to make tools, to build fires, to create art, to write these words. All of it possible because 6 million years ago, some hominin decided that walking on two legs, as awkward and risky as it was, offered advantages that outweighed the costs. They were right. Your brain is expensive. Right now, as you're listening to this, the 3 pounds of tissue inside your skull is consuming about 20% of your body's total energy, even though it represents only 2% of your body weight. It's burning through glucose and oxygen at a rate that would be unsustainable. Your brain is a metabolic furnace, demanding constant fuel, never sleeping, always active. This creates a problem. A big problem. How do you feed an organ that costs this much to run? And here's the evolutionary puzzle that kept scientists arguing for decades. How did our ancestors afford to grow brains that got bigger and bigger, more and more expensive, generation after generation, until they tripled in size over just a few million years? The answer is food. Specifically, what kind of food you eat and how you prepare it. Because somewhere between 2 and 3 million years ago, our ancestors made dietary changes that provided the caloric surplus needed to fuel the most dramatic brain expansion in mammalian history. They started eating more meat, and critically, they started cooking. Let's start with meat, because that comes first in the timeline. Around 2.5 million years ago, we see the emergence of the genus Homo. Homo habilis, the earliest member of our genus, had a brain about 600 cubic centimeters, significantly larger than Australopithecus, but still only about half the size of modern humans. And the archaeological evidence suggests these early Homo were consuming meat regularly, systematically, not just opportunistically. How do we know? Cut marks on bones. Thousands of animal bones from sites across East Africa, showing stone tool marks where hominins sliced through flesh, scraped meat from bone, cracked open long bones to access marrow. The pattern is unmistakable. These weren't scavengers stealing a few scraps. These were hominins, processing entire carcasses, methodically extracting every calorie. But here's the question that divided scientists for years. Were they hunting? The evidence suggests both, probably varying by opportunity and capability. Some of the bones show tooth marks from carnivores overlaid by stone tool marks, suggesting hominins were second to the carcass, scavenging after the initial predator had eaten its fill. But other bones show tool marks with no carnivore damage, suggesting hominins had first access, either through hunting or getting to a carcass before other scavengers. Either way, the key point is this: meat became a regular, significant part of the hominin diet, and meat changes everything metabolically. Here's why. Plant foods, the primary diet of most primates, require extensive processing by the digestive system. Leaves, roots, fruits, they're full of cellulose and complex carbohydrates that take time and energy to break down. Gorillas and other herbivorous primates have huge guts, long intestines filled with bacteria that ferment plant material for hours or days. The digestive system itself is metabolically expensive, constantly working, demanding energy. Meat is different. It's nutrient-dense, rich in proteins and fats, easy to digest compared to tough plant material. A carnivore's digestive tract can be shorter and simpler because meat doesn't require the same extensive processing. This is where the expensive tissue hypothesis comes in. The idea, proposed by anthropologists Leslie Aiello and Peter Wheeler, is that organs compete for energy. The brain and the gut are both metabolically expensive. Growing a larger brain requires shrinking something else, and our ancestors' guts got smaller as their brains got bigger. Shorter intestines, simpler digestive systems, trading digestive capacity for cognitive capacity. This trade only works if you're eating high-quality food that's easy to digest. Food like meat, the calories you save by having a smaller gut can be redirected to feeding a larger brain, but you need a reliable source of those high-quality calories, or the whole system collapses. This is where hunting and scavenging strategies become crucial. Early Homo had to become skilled at acquiring animal protein regularly enough to support their expanding brains. Stone tools were essential for this. Without tools, accessing meat from large carcasses is nearly impossible. Human teeth and hands can't tear through thick hide, but a sharp stone flake can. Within minutes, a hominin with good tools could butcher a carcass, extract the meat and marrow, and carry it to safety before larger predators arrived. The archaeological evidence shows this happening. Around 2 million years ago, we see the appearance of Homo erectus, a species with a brain averaging about 900 to 1,000 cubic centimeters, approaching the lower range of modern human brain size. And Homo erectus wasn't just eating meat. They were specialists at it. Their bodies show adaptations for long-distance walking and running. Their tools show increasing sophistication. Everything about Homo erectus suggests a lifestyle built around ranging widely across the landscape, hunting or scavenging large game, processing it efficiently, and sharing it within their social groups. But meat alone doesn't fully explain the brain expansion, because there's another factor, perhaps even more important than the shift to meat eating. This is where things get really interesting, because cooking is a form of external digestion. When you cook food, you're breaking down proteins and carbohydrates before they enter your mouth. You're doing with fire what your gut would otherwise have to do chemically. This makes nutrients more bioavailable, easier to extract, requiring less digestive effort. The question is, when did hominins start cooking? The answer is frustratingly uncertain, because fire doesn't preserve well in the archaeological record. Charcoal can survive, but proving it came from a deliberately controlled fire rather than a natural wildfire is difficult. The earliest clear evidence of controlled fire use dates to around 400,000 years ago. Hearths, deliberately constructed fire pits, arrangements of stones to contain flames, burned bones, showing systematic heating. By this time, fire use was definitely widespread and systematic, but some researchers think cooking might go back much further, perhaps 1.5 to 2 million years ago, coinciding with the appearance of Homo erectus. The evidence is indirect. Changes in tooth size and jaw structure suggesting less mechanical processing of food. Anatomical changes in the gut, the sheer size of Homo erectus brains requiring caloric inputs that seem difficult to achieve without cooking. Anthropologist Richard Wrangham argues that cooking is the key innovation that made us human. His book, Catching Fire: How Cooking Made Us Human, lays out the case that cooked food provided the energy surplus that enabled everything else. Bigger brains, smaller guts, social changes around shared meals, the development of home bases where groups would gather around fires. Think about what cooking does. A raw potato is tough, starchy, difficult to digest. Cook it and the starches gelatinize, breaking down into sugars your body can easily absorb. Raw meat is tough and requires extensive chewing. Cook it and proteins denature, making it tender and easier to digest. The caloric return on investment increases dramatically when food is cooked. This would have been revolutionary. A group of Homo erectus hunting or scavenging a large animal could bring it back to their fire, cook the meat, and extract far more calories than they could from eating it raw. The fire would also allow them to dry meat for storage, creating food security. They could cook tough plant foods that would otherwise be inedible, expanding their dietary options. And there's another factor that Wrangham emphasizes. Cooking is social. You can't really cook individually with primitive technology. Fire requires maintenance, fuel gathering, protection from wind and rain. It makes sense to have a central fire that a group shares. This creates a focal point for social interaction. People gathering around the fire to cook and eat together, sharing food, telling stories, strengthening social bonds. The neuroscience supports the dietary hypothesis too. Brain tissue is metabolically expensive, but not all brain growth is equal. What matters is what kind of brain tissue you're growing. The expansion in Homo wasn't just making the brain bigger overall. It was disproportionately expanding certain regions. The prefrontal cortex grew substantially. This is the part of the brain responsible for planning, decision-making, impulse control, social behavior. The temporal lobes expanded, involved in memory, language processing, complex auditory information. The parietal regions grew, handling spatial reasoning, tool use, abstract thought. These aren't the regions that control basic survival functions. Those were already well developed in earlier hominins. These are the regions that enable complex, uniquely human cognition. And growing them requires not just calories but specific nutrients. Proteins, omega-3 fatty acids, iron, zinc, B vitamins, the kind of nutrients abundant in meat, and especially abundant in certain organ meats and bone marrow. There's even a neurochemical angle to this story. Meat contains high levels of certain amino acids that are precursors to dopamine, a neurotransmitter crucial for motivation, reward processing, and learning. Some researchers have proposed that increased dietary protein, especially from meat, led to expanded dopaminergic systems in the brain. Dopamine does interesting things. It drives exploration and novelty seeking. It reinforces behaviors that lead to rewards. It helps with working memory and cognitive flexibility. It's involved in fine motor control, which is essential for tool making. An expanded dopaminergic system would make hominins more innovative, more willing to try new behaviors, better at learning from experience. This creates another feedback loop. Better diet leads to brain changes that make you better at acquiring that diet. The hominin who can plan a hunt more effectively, who can remember where prey animals gather at different seasons, who can innovate new hunting techniques. That hominin acquires more food. More food supports further brain development in the next generation. Round and round. But let's be clear about something. Meat, eating, and cooking didn't cause larger brains directly. Evolution doesn't work that way. What happened was that environmental and dietary changes removed constraints. When your ancestors were eating mostly plants and had to spend most of their day chewing and digesting, there was a metabolic ceiling on how big the brain could get. The body couldn't afford to maintain both a large brain and a large gut. But when diet shifted to include more meat, and especially when cooking made food easier to digest, that ceiling lifted. Now there was metabolic room for the brain to grow. And once that room existed, any genetic mutations that increased brain size could be selected for if they provided cognitive advantages. Better problem solving, better social navigation, better memory, better tool making. These advantages would have been significant in the challenging environments where our ancestors lived. The timeline supports this interpretation. Brain size increases happen in steps, not gradually. There's a jump when Homo appears, around 2.5 million years ago. Another jump with Homo erectus around 2 million years ago. Another expansion leading to Homo heidelbergensis around 600,000 years ago. And finally, modern Homo sapiens, with brains averaging 1,350 cubic centimeters, appearing around 300,000 years ago. Each of these steps corresponds with archaeological evidence of dietary or technological changes, better tools for processing carcasses, evidence of fire use, remains of hunted animals showing increasing sophistication in hunting strategies. The pattern is clear. Diet and brain size co-evolved, each enabling the other. And here's the remarkable thing. The human brain stopped growing. Around 300,000 years ago, brain size reached roughly modern levels and hasn't increased since. Why? Probably because we hit another ceiling. Not a metabolic one this time, but a biomechanical one. Female pelvic anatomy can only accommodate so large an infant head during birth. Making babies' heads bigger would make childbirth even more dangerous and difficult than it already is. So evolution found a different solution. Instead of making brains bigger, make them better. More connections between neurons, more efficient neural architecture, extended childhood learning periods, cultural transmission of knowledge across generations. You can increase cognitive capacity without increasing physical brain size, but all of that later sophistication was built on a foundation laid millions of years earlier. When dietary changes removed the metabolic constraints that had kept hominin brains small for millions of years, the hunger that built our brains wasn't just physical hunger, though that was certainly part of it. It was the evolutionary drive to acquire better food sources, to process them more efficiently, to extract more calories and nutrients from the environment. That drive shaped our bodies, our brains, our behaviors. It turned tree-dwelling apes into terrestrial hunters and gatherers. It sparked technological innovation and social cooperation. Every thought you have, every memory, every moment of consciousness, all of it runs on a brain that exists because your ancestors millions of years ago figured out how to acquire and process high-quality food. They became meat-eaters. They mastered fire. They learned to cook. And in doing so, they created the metabolic conditions that allowed 3 pounds of the most complex tissue in the known universe to develop inside a skull. You are, quite literally, made of the food your ancestors ate and the fires they tended. The brain reading these words, processing these ideas, is the direct result of dietary choices made by creatures who lived and died millions of years before humans as we know them existed. They were hungry. They found solutions, and those solutions built your mind. Close your eyes for a moment and try to think about thinking. Try to observe your own mind as it processes information, makes decisions, plans for tomorrow, remembers yesterday. This ability, this recursive self-awareness, this capacity to think about the fact that you're thinking, is something that exists nowhere else in nature at this level of sophistication. And it all happens inside a structure that tripled in size over the course of just 3 million years. 3 million years sounds like forever, but in evolutionary terms, it's an eye blink. But hominin brains exploded in size at a rate that's almost unprecedented in the fossil record. From the 450 cubic centimeters of Australopithecus to the 1,350 cubic centimeters of modern humans, that's not gradual drift. That's rapid, directional selection. Something was driving brain expansion with extraordinary force. The question is, what were these expanding brains actually doing? Because size alone doesn't tell the whole story. A brain isn't just a bigger computer running the same programs faster. As hominin brains grew, they were also reorganizing, developing new structures, creating new capabilities. The mind that emerged wasn't just a scaled-up ape mind. It was something fundamentally different. Let's start with the anatomy, because that's what we can see in the fossil record. Paleoanthropologists study endocasts, molds of the inside of fossil skulls that preserve the shape of the brain that once filled them. These endocasts reveal not just volume but also surface features, the bumps and wrinkles that indicate which parts of the brain were expanding. In Australopithecus, the brain shape is distinctly ape-like. The frontal regions are relatively small. The visual cortex at the back of the brain is proportionally large, as it is in other primates. The overall organization suggests a brain optimized for the challenges faced by an intelligent ape. Social navigation within a troop, recognition of food sources, basic problem-solving. But nothing extraordinary. Then Homo habilis appears around 2.5 million years ago, and we start seeing changes. The frontal lobes are expanding. The parietal regions are getting larger. The brain is still small by modern standards, only about 600 cubic centimeters, but the proportions are shifting. More neural real estate is being devoted to functions that aren't purely about immediate sensory processing or motor control. By the time we get to Homo erectus, around 2 million years ago, the changes are dramatic. Brain volume has jumped to 900 or even 1,000 cubic centimeters. The frontal cortex is substantially larger. The temporal lobes have expanded. The overall brain shape is starting to look more human than ape-like. And this coincides with archaeological evidence of more sophisticated behavior, better tools, evidence of fire use, wider geographic distribution suggesting these hominins could adapt to diverse environments. But here's where it gets tricky. Brain size and cognitive ability don't scale linearly. A brain twice as large isn't necessarily twice as smart. What matters is organization, connectivity, efficiency, the way different brain regions communicate with each other, the density of neural connections, the ratio of neurons to support cells. Modern neuroscience has revealed something fascinating about Homo erectus brains that we couldn't have known just from looking at endocasts. Studies of preserved infant Homo erectus skulls show that their brains develop differently than modern human brains. In humans, the brain continues growing rapidly after birth, following a fetal growth pattern for the first year of life. This extended period of rapid brain development is unique to our species, and it's crucial for cognitive development. But Homo erectus infants appear to have had brain growth patterns more similar to apes. Their brains grew quickly in utero, but slowed down more rapidly after birth. This suggests that despite having large brains, Homo erectus may have had different cognitive capabilities than modern humans. Their brains were big, but they weren't wired quite the same way. This raises a profound question. When did the modern human mind emerge? When did brains stop just getting bigger and start getting fundamentally different in how they functioned? The evidence suggests it happened relatively late, perhaps as recently as 300,000 years ago with the emergence of Homo sapiens. This is when we see brain sizes reaching modern levels. But more importantly, this is when the archaeological record starts showing evidence of distinctly modern behavior. But let's back up and think about what a larger, more complex brain actually enables. What cognitive abilities emerge as the prefrontal cortex expands, as the temporal lobes develop, as neural networks become more interconnected? Planning is the big one, the ability to envision a future state and work backward to figure out the steps needed to achieve it. This requires holding multiple pieces of information in working memory simultaneously. It requires imagining scenarios that don't currently exist. It requires suppressing immediate impulses in favor of delayed gratification. The prefrontal cortex is central to all of this. It's the brain's executive control center, coordinating information from other brain regions, making decisions, planning sequences of actions. In apes, the prefrontal cortex is relatively small. In humans, it's massive, comprising about 30% of the total brain volume. This expansion happened gradually over millions of years, but the behavioral implications were revolutionary. Consider what planning means for toolmaking. The earliest Oldowan tools could be made more or less spontaneously. See a problem, grab a rock, make a tool, use it immediately. But later tools, particularly the hand axes of the Acheulean tradition starting around 1.7 million years ago, required planning. You had to select the right kind of stone, not just any stone, but one with the right properties. You had to execute a sequence of carefully controlled strikes, each one setting up the next. Making an Acheulean hand axe could take hundreds of individual flaking strikes, each requiring precision and foresight. Mess up early in the sequence and you've wasted all that effort. This is sequential planning at a level that requires a sophisticated prefrontal cortex. And Homo erectus was doing this routinely, over and over, creating tools of remarkable symmetry and consistency. Memory is another crucial capability. Not just remembering where you found food last week, though that's important. We're talking about episodic memory, the ability to mentally travel back in time and re-experience past events. To remember not just what happened, but when and where and who was involved. To use those memories to predict future situations. The temporal lobes, particularly the hippocampus, are central to memory formation and recall. These regions expanded substantially in Homo erectus, and continued expanding in later species. Better memory means better learning. It means accumulating knowledge over a lifetime and potentially sharing that knowledge with others. It means recognizing patterns over long timescales, understanding seasonal changes, remembering multi-year cycles. For a hunter-gatherer, memory is survival. Remembering where certain plants fruit in which season. Remembering migration patterns of prey animals. Remembering which water sources are reliable during drought. Remembering social debts and alliances within the group. All of this requires robust, flexible memory systems. Abstract thought is perhaps the most mysterious cognitive capability, and it's the hardest to track in the fossil record because it doesn't leave obvious archaeological traces. But we can infer its emergence through proxy evidence. When do we start seeing symbolic objects? When do we see evidence of ritual behavior? When do we see art? Abstract thought requires the ability to let one thing stand for another thing. A sound can represent an object. A mark on a stone can symbolize an idea. This capacity, called symbolic representation, seems to be uniquely human. No other animal does it naturally at anywhere near our level. The question is when it emerged. Some researchers think symbolic thought appeared very early, perhaps with Homo erectus. Others think it's a late development, only appearing with anatomically modern humans in the last few 100,000 years. What we do know is that by 50,000 years ago, symbolic thought was definitely present and widespread. Cave paintings, carved figurines, shell beads, burial goods, the archaeological record explodes with symbolic objects. This is sometimes called the Upper Paleolithic Revolution, or the Great Leap Forward, a period when behavioral modernity seems to suddenly appear in the archaeological record. But here's the thing about the Great Leap Forward. It might not be so sudden after all. More recent discoveries keep pushing evidence of symbolic behavior further back in time. Ochre pigments show up in sites hundreds of thousands of years old. Shell beads dated to over 100,000 years ago. Possible deliberate burials by Neanderthals. The revolution might have been more gradual than it first appeared, or it might have happened multiple times in different populations. What's clear is that at some point, hominin brains became capable of thoughts that transcend immediate physical reality. They could imagine gods and spirits. They could create art for its own sake. They could develop complex social rituals. They could tell stories. These aren't just nice extras. These capabilities are cognitively demanding. They require neural architecture sophisticated enough to maintain multiple levels of representation simultaneously. To know that this object is a rock, but it also represents my ancestor, and interacting with it in this particular way honors that ancestor, which strengthens social bonds, which provides survival advantages. That's a lot of abstract layers. Social cognition is another dimension of the expanding brain that often gets overlooked. Humans are intensely social animals. Our survival depends on navigating complex social networks, understanding other people's minds, cooperating with non-relatives, maintaining long-term relationships, managing reputations. The social brain hypothesis proposes that much of human brain expansion was driven by the demands of living in large, complex social groups. As groups got bigger, social navigation became more challenging. You need to remember who you can trust, who owes you favors, who's allied with whom, who's trying to cheat you. You need theory of mind, the ability to understand that other people have thoughts and intentions different from your own. The archaeological evidence shows that hominin group sizes were increasing over time. Earlier, hominins probably lived in groups of 20 to 30 individuals, similar to modern chimps. But by the time of Homo erectus, groups were likely larger, perhaps 50 to 100 individuals. Modern human hunter-gatherers often live in groups that fluctuate between 30 and 150 members. Managing social relationships in groups of that size requires serious cognitive horsepower. British anthropologist Robin Dunbar proposed that there's a relationship between primate brain size and typical group size. Larger brains can maintain more social relationships. For humans, Dunbar's number is around 150, the number of stable relationships you can meaningfully maintain. Coincidentally, this matches the typical size of hunter-gatherer bands. All of these cognitive capabilities, planning, memory, abstract thought, social cognition, they don't exist in isolation. They interact, reinforce each other, create emergent properties that are greater than the sum of parts. This is what makes the human mind unique. Not any single capability, but the integration of multiple sophisticated systems. Language is probably the ultimate integrative capability, bringing together vocalization, symbolic thought, social cognition, memory, and planning into a communication system unlike anything else in nature. We'll explore language in detail in the next chapter, but it's worth noting here that language almost certainly co-evolved with these other cognitive advances. You can't have complex language without sophisticated memory, abstract thought, and social awareness. And language, once it emerges, supercharges all those other capabilities. The Homo erectus brain, despite being nearly as large as modern human brains, probably couldn't support full modern language. The differences in developmental timing, in neural organization, in the proportions of different brain regions, all suggest that Homo erectus thought differently than we do. They were smart, adaptive, successful for over 1 million years. But they weren't us. Not quite. Somewhere between Homo erectus and modern Homo sapiens, the final pieces fell into place. The brain reached its current size and organization. Developmental patterns shifted so that brains continued growing rapidly after birth, allowing childhood learning to shape neural architecture. The prefrontal cortex reached its modern proportions, enabling extended planning and executive control. The temporal lobes developed the capacity for rich episodic memory and language processing. And consciousness changed, not just in degree but potentially in kind. The recursive self-awareness that lets you think about your own thinking. The ability to imagine not just what is, but what could be. The capacity to mentally time travel, to remember the past and envision the future. To create meaning and purpose where none objectively exists. This is what separates the human mind from the ape brain. Not the size, though that matters. Not any single feature, though many are important. It's the whole integrated system, organized in a way that creates something unprecedented. A mind that can look at itself, that can question its own existence, that can wonder about its origins. The brain you're using right now to process these words is the product of 3 million years of relentless evolution, driven by environmental challenges, dietary changes, social pressures, and feedback loops between technology and biology. Every neuron, every synapse, every circuit is the result of countless generations of hominins whose brains were slightly better at solving the problems their worlds presented. They didn't know they were evolving toward anything. They were just living, surviving, reproducing. But the cumulative effect of millions of years of selection created something that transcends its origins. A mind capable of contemplating deep time, of understanding evolution, of wondering how it all began. You are the universe become conscious of itself. Say something, anything, out loud, even just a whisper. Feel your breath moving up from your lungs, through your vocal cords, shaped by your tongue and lips and teeth into sounds that carry meaning. Now think about what just happened. You took an abstract thought, a concept existing only in your mind, and encoded it into vibrations in the air. And if someone else were listening, their ears would capture those vibrations, their brain would decode them, and the thought that originated in your mind would reconstruct itself in theirs. This is language, and it's arguably the most important innovation in human evolution. More important than tools, more important than fire, more important even than the big brain that makes language possible. Because language is what transforms isolated individual intelligence into collective cultural knowledge. It's what lets one generation transmit everything it learned to the next. It's what makes you human in a way that nothing else quite does. But here's the mystery that has haunted anthropologists, linguists, and evolutionary biologists for over a century. When did language emerge? How did it develop? Did it appear suddenly or gradually? And here's the most frustrating part. Language doesn't fossilize. We can find bones and tools from millions of years ago, but the words our ancestors spoke vanished the moment they were uttered. We're left trying to reconstruct the evolution of language from indirect evidence, anatomical clues, and informed speculation. Let's start with what we can see, the anatomy. Modern humans have a suite of physical adaptations that make complex speech possible. These adaptations are visible in the fossil record, or at least their traces are, which gives us some clues about when language might have emerged. The first critical feature is the position of the larynx, the voice box. In humans, the larynx sits low in the throat, lower than in any other primate. This creates a long pharyngeal cavity, the space above the larynx where sounds can be modulated and shaped. This configuration allows for the production of a wide range of distinct vowel sounds. You can make an R sound, an E sound, an U sound, all clearly different from each other. In chimps and other apes, the larynx sits higher in the throat, positioned so they can breathe and drink at the same time. Human babies are born with high larynxes too. This lets them breathe while nursing. But around 2 years old, the larynx descends to its adult position. We sacrifice the ability to breathe and drink simultaneously for the ability to speak. Can we tell where the larynx was positioned in fossil hominins? But we can look at the base of the skull, where muscles attached to the larynx leave marks on bone. Changes in skull base shape suggest that the larynx was descending over evolutionary time, though pinpointing exactly when is difficult. Most researchers think Homo erectus probably had a somewhat descended larynx, intermediate between apes and modern humans. This would have given them greater vocal range than earlier hominins, but perhaps not the full flexibility of modern speech. Neanderthals, our closest extinct relatives, probably had vocal anatomy very similar to ours, capable of producing the full range of human speech sounds. The tongue is another crucial component. Human tongues are uniquely shaped, thick and muscular, capable of fine motor control that allows rapid, precise movements. The tongue is controlled by the hypoglossal nerve, which passes through a canal in the skull base called the hypoglossal canal. In humans, this canal is larger than in apes, presumably to accommodate more nerve fibers controlling more complex tongue movements. Measurements of hypoglossal canal size in fossil hominins show expansion happening relatively recently, perhaps within the last 500,000 years. This suggests that the fine motor control needed for rapid speech is a late development, not something that emerged with early Homo. Breath control matters too. Speaking requires precise regulation of airflow from the lungs. You need to be able to sustain exhalation for several seconds while modulating pressure and volume. This is controlled by muscles between the ribs and by the diaphragm. In modern humans, the thoracic vertebrae have larger neural canals than in apes, allowing for more nerve connections to these breathing muscles. Fossil evidence suggests this expansion happened sometime in the last few 100,000 years, again pointing to relatively recent development of the full speech apparatus. Homo erectus probably had some degree of breath control beyond what apes have, but not at modern levels. Then there's the brain itself. Language processing in modern humans involves specific brain regions, most notably Broca's area in the frontal lobe, responsible for speech production, and Wernicke's area in the temporal lobe, responsible for comprehension. Endocasts of fossil skulls show that these regions were expanding over time, but interpreting this is tricky because brain organization doesn't perfectly follow external shape. What's clear is that by the time of Homo heidelbergensis, around 600,000 years ago, the anatomical pieces for complex speech were mostly in place. The descended larynx, the controlled breathing, the brain regions, all present or developing. This doesn't prove language existed at that point, but it suggests the hardware was there. But anatomy only tells part of the story. Because here's the thing about language. It might not have started with speech at all. It might have started with gestures. Think about how you communicate without words. You point at things. You mime actions. You use facial expressions to convey emotions. These are all forms of symbolic communication that don't require vocalization, and they come naturally to humans in a way they don't to other animals. Great apes can learn simple sign language in captivity. Chimps like Washoe and Koko the gorilla famously learn to use hundreds of signs, but they don't spontaneously develop gestural communication in the wild beyond very basic signals. Even deaf children who've never been exposed to formal sign language will spontaneously create their own gestural systems, complete with grammar and syntax. Some researchers argue that language began as a gestural system, only later adding vocalization. The advantages of gesture are obvious. You can communicate silently, useful when hunting or hiding from predators. You can signal across distances too far, for voice to carry clearly. The archaeological evidence provides some support for this idea. The same brain regions that control language in modern humans also control fine motor movements of the hands. Broca's area, the speech production center, is also involved in sequential manual actions like toolmaking. This suggests deep evolutionary connections between hand coordination and language. Homo erectus was making sophisticated tools that required precise hand movements and sequential planning. The cognitive architecture for gesture-based communication might have emerged alongside these toolmaking abilities. Imagine an expert toolmaker showing a novice how to create a hand axe. Words would be useless without a shared vocabulary. Over time, vocalizations might have been added to supplement gestures. Grunts and calls to get attention, sounds that represent specific objects or actions. Gradually, the vocal component becomes more complex, more flexible, until eventually it can carry most of the communicative load, freeing the hands for other tasks. But this is all speculation. We don't know if language developed gesture first or voice first or both simultaneously. What we do know is that by 50,000 years ago, maybe earlier, fully modern language almost certainly existed. The behavioral complexity we see in the archaeological record from this period, the art, the long-distance trade networks, the rapid innovation, all of it strongly suggests sophisticated communication. Language does more than just communicate information. It changes how you think. Linguists and cognitive scientists debate whether language shapes thought or thought shapes language, but everyone agrees they interact powerfully. Consider numbers. Without language, you can perceive quantity in rough ways, more or less, many or few. But precise counting requires linguistic labels: 1, 2, 3, 4. These aren't natural categories. They're cultural constructs transmitted through language, and once you have linguistic number concepts, you can perform mental mathematics that would be impossible otherwise. Or think about time. Past, present, future. These aren't things you can point at. They're abstract concepts that exist primarily in language. Being able to talk about yesterday and tomorrow changes how you plan, how you remember, how you conceive of your own existence as extending through time. Language also enables collaborative problem-solving at levels impossible for non-linguistic creatures. You can describe a problem to someone who hasn't experienced it directly. You can propose solutions and debate their merits. You can combine multiple perspectives to develop approaches that no individual would have conceived alone. This is cumulative culture, the ability to build on previous generations' knowledge, and it requires language. The most profound impact of language might be on social cohesion. Language allows for gossip, the sharing of information about who's trustworthy, who's cheating, who's forming alliances with whom. This might sound trivial, but it's actually crucial for maintaining cooperation in large groups. When everyone knows that their reputation matters, that antisocial behavior will be talked about and remembered, it creates pressure to cooperate even with people you're not related to. Language enables storytelling, which is how cultures transmit values, history, and identity across generations. Every human society has origin myths, moral tales, histories of great deeds, and terrible failures. These stories shape behavior, create shared identity, define what the group values and condemns. Without language, this cultural transmission is severely limited. And perhaps most mysteriously, language might be what enables the kind of recursive, self-aware consciousness that characterizes human experience. To think in words about your own thoughts, to ask questions like, "Who am I?" and "Why am I here?" These might all depend on having linguistic structures to hang consciousness on. When did all of this emerge? The honest answer is we don't know precisely. The anatomical evidence suggests the physical capacity for speech was developing over hundreds of thousands of years. The behavioral evidence suggests something like modern language existed by 50,000 years ago at the latest, and possibly much earlier. Some researchers think language emerged quite recently, perhaps within the last 100,000 years, and that its appearance triggered the behavioral revolution we see in the archaeological record. The sudden flowering of art, symbolism, and innovation might reflect the power of language to transform cognition and culture. Others argue for deeper origins. Maybe proto-language existed in Homo erectus, simple symbolic communication that gradually elaborated over 1 million years. Maybe Neanderthals had full language, given their sophisticated anatomy and behavior. Maybe multiple hominin species independently developed linguistic abilities. The truth is probably somewhere in between, and it probably wasn't a single sudden transition. More likely, communicative complexity increased gradually, with each innovation building on the last. Simple calls became more symbolic. Gestural communication became more elaborate. Vocalizations gained flexibility. Syntax emerged to organize sequences of signals. Grammatical complexity increased, each step providing advantages that selection could act on. What we can say with confidence is that by the time anatomically modern humans were spreading out of Africa and across the world, they had language. Fully modern, syntactically complex language, capable of expressing any thought, describing any experience, transmitting any cultural knowledge. This communication system gave them advantages that no other hominin could match. With language, humans could coordinate hunts with precision, could share detailed environmental knowledge, could teach complex skills efficiently, could maintain alliances across time and space, could create and transmit culture at a pace that biological evolution could never match. Within a few thousand generations, they went from one hominin species among many to the only ones left standing. The words you're hearing right now, processed by neural circuits that evolved specifically for language comprehension, are part of an unbroken chain stretching back tens of thousands of years, maybe hundreds of thousands. Every generation speaking to the next, teaching them not just to survive, but to think, to wonder, to question. Language made us human. Not in the biological sense, that was a gradual process spanning millions of years, but in the cultural sense, in the sense of being creatures who live primarily in worlds of meaning we create through communication. The species that can say, "I think, therefore I am," and understand what that means. And somewhere in the Stone Age, our ancestors discovered they could turn air into meaning, silence into connection, thoughts into shared reality. They spoke, and the world has never been silent since. Imagine standing in complete darkness. Not the darkness of your bedroom at night, but absolute, perfect blackness. The kind of darkness that exists deep underground, where no light has penetrated for thousands of years. You're in a cave, narrow passages winding behind you for hundreds of meters. The air is cool and damp. Water drips somewhere in the distance. And in your hand, you hold a flickering torch. Now imagine raising that torch to the cave wall and seeing animals. Not crude stick figures, but rendered with exquisite detail. Horses galloping across the stone, bison with shaggy coats and curved horns, lions prowling, bears standing, deer leaping. The images seem to move in the firelight, shadows dancing, bringing ancient creatures to life on the rock face. This is what happened when archaeologists first entered caves like Lascaux in France, Altamira in Spain, Chauvet Cave in the Ardèche region. They discovered something that changed our understanding of human evolution forever. They found proof that our ancestors didn't just survive, they created. They imagined, they dreamed in color, and made those dreams permanent. Cave art represents something profound in human evolution. It's evidence of symbolic thought operating at full power. It's proof that the people who made these images saw the world not just as it was, but as it could be represented. That art could capture motion, emotion, meaning beyond mere survival. The oldest confirmed cave paintings date back over 60,000 years, possibly longer. Some researchers claim that simple geometric markings and hand stencils in caves in Spain and Indonesia might be even older, perhaps made by Neanderthals rather than modern humans. If true, this would mean symbolic expression emerged independently in multiple hominin species, suggesting it's a threshold that advanced minds naturally cross. But let's focus on the spectacular painted caves of Europe, because these give us the clearest window into the minds of late Stone Age humans. Chauvet Cave in France contains some of the oldest elaborate paintings yet discovered, dated to around 36,000 years ago. When researchers first entered this cave in 1994, they expected to find crude early attempts at art. Instead, they found masterpieces. The artists at Chauvet understood perspective. They used the natural contours of the cave wall to give their animals three-dimensional form. They showed movement by painting multiple sets of legs on a single body, creating the illusion of running. They used shading, scratching away charcoal to create lighter tones, building up layers for darker areas. These weren't primitive scribblings. This was sophisticated artistic technique. The animals depicted are fascinating too. Not just the species humans hunted for food, though those appear, but also dangerous predators that were rarely, if ever, part of the human diet. Cave lions, cave bears, rhinoceroses, animals that would have been threats, not prey. Why depict them? Why spend hours in dangerous, dark caves painting creatures that could kill you? We don't know. We can't know. The people who made this art left no written explanation, no oral tradition that survived 40,000 years. We're left to interpret, to speculate, to project our own assumptions onto images created by minds that were fully human but existed in a world utterly alien to ours. Some theories suggest the paintings had ritual or religious significance. Maybe depicting dangerous animals was a form of sympathetic magic, an attempt to gain power over them. Maybe the caves were sacred spaces, the paintings created during vision quests or shamanic journeys. The deep, dark chambers might have been viewed as portals to a spirit world, the painted animals representing spirit guides or totems. Other theories are more practical. Maybe the paintings were teaching tools, ways of passing down knowledge about animal behavior and hunting techniques to younger generations. Look at how the bison stands when it's about to charge. See how the horse holds its head when it's alert to danger. This is visual information storage, a way of preserving crucial survival knowledge, or perhaps it was simply art for art's sake. The human impulse to create, to make beauty, to leave a mark saying, "I was here, I existed, I saw these things and made them permanent." This impulse exists in every human culture ever documented. Children start drawing spontaneously. Adults create art, even when there's no practical reason to do so. Maybe our Stone Age ancestors were no different. What strikes modern viewers most is the skill involved. These artists understood their materials intimately. They created pigments from minerals, grinding ochre and hematite for reds and yellows, using manganese dioxide and charcoal for blacks. They mixed these pigments with binding agents, possibly animal fat or plant resins, creating paints that have lasted tens of thousands of years. They prepared their surfaces, sometimes scraping clean areas of wall, smoothing them before painting. They used different techniques for different effects. Finger painting for some images, brushes, probably made from animal hair or plant fibers, for fine details, blowing pigment through hollow bones to create stenciled effects, even using their mouths to spray paint, creating hand stencils by placing a hand on the wall and blowing pigment around it. These hand stencils are particularly moving. They're the most direct connection we have to individual humans from the deep past. A negative image of someone's hand, made by a person standing exactly where you're standing, raising their hand to the wall just as you might. Recent analysis of hand stencils from various caves suggests they include hands of women, men, and children. Entire communities were participating in this artistic practice. But cave paintings aren't the only evidence of symbolic thought in the Stone Age. Carved figurines appear in the archaeological record around the same time. The Lion Man, discovered in Germany, is perhaps the most remarkable. Carved from mammoth ivory around 40,000 years ago, it depicts a figure that's part human, part lion, a therianthrope, a mythological being that combines human and animal features. Think about what creating this figure required cognitively. The artist had to imagine something that doesn't exist in nature. They had to hold that imagined form in mind while executing hundreds of hours of careful carving. They had to have a concept of the sacred or supernatural that could be represented in physical form. This is abstract thought operating at the highest level. Female figurines, often called Venus figurines, appear across Europe from around 30,000 years ago. Small, portable sculptures depicting women with exaggerated anatomical features, breasts, hips, bellies, emphasized. These have been interpreted as fertility symbols, mother goddesses, portable erotic art, even self-portraits made by women looking down at their own bodies. But their widespread distribution suggests they held significant cultural meaning. Body decoration is another form of symbolic expression. Ochre, that red mineral pigment, shows up in archaeological sites going back hundreds of thousands of years. Early finds might represent practical use, ochre as a tanning agent for hides or as an adhesive component. But by 70,000 years ago in South Africa, we find clear evidence of ochre being used for symbolic purposes. Shell beads, deliberately perforated and strung together, appear in sites across Africa and the Middle East dating back over 100,000 years. The shells often came from coastal areas and were transported inland, sometimes hundreds of kilometers. They were carefully perforated without breaking, then worn as necklaces or sewn onto clothing. This is personal adornment, decoration with no practical survival function, created purely for social or aesthetic reasons. What does body decoration signal? Status, identity, group membership, individual personality. In modern hunter-gatherer societies, body decoration serves all these functions. It marks life stage transitions, identifies clan affiliations, displays personal achievements. It transforms the human body into a canvas for cultural information. Our Stone Age ancestors were almost certainly using decoration the same way. That string of shell beads wasn't just pretty, it was a statement. I belong to this group. I've achieved this status. I have the resources and social connections to acquire these rare materials. I'm someone worth paying attention to. Symbolic thought and artistic expression didn't emerge in isolation. They're connected to everything else we've discussed. Larger brains creating the neural capacity for abstract representation. Language providing a framework for shared meanings. Social complexity creating needs for identity markers and group symbols. Better diets providing the caloric surplus to support specialists who could dedicate time to creating non-utilitarian objects. But there's something else happening here too. Something that goes beyond practical explanation. These cave paintings, these carved figurines, these shell beads, they represent humans trying to understand their place in the world, trying to make sense of existence, trying to create meaning where none objectively exists. The human condition is unique in this regard. We alone, among all species, know that we will die. We alone look at the stars and wonder if anyone's looking back. This existential awareness, this search for meaning, it's written all over the symbolic objects from the Stone Age. A cave painting of a handprint says, "I existed, I was here, remember me." Our imagination exceeds what our eyes can see. A string of carefully crafted beads says, "Beauty matters, status matters. I am not just a survival machine, but a person with identity and worth." The emergence of symbolic thought represents the final piece falling into place in the puzzle of human uniqueness. Tool use alone doesn't make us human. Big brains alone aren't enough. Neanderthals had brains as large as ours. Even language, crucial as it is, might have existed in simpler forms in other hominins. But symbolic thought, at this level, the ability to create meaning, to build entire worlds of imagination, and then externalize them through art and ritual and decoration. This seems to be uniquely and universally human. Every culture creates art. Every culture has music. Every culture tells stories. Every culture marks important life events with ritual and symbol. The cave painters of Chauvet and Lascaux were our direct ancestors. Not metaphorically, but literally. The people who walked into those dark caves 40,000 years ago, who mixed their pigments and raised their torches and painted those magnificent animals, they had the same DNA you do, the same brain structure, the same capacity for wonder and creativity, and the desperate need to leave something permanent in an impermanent world. If you could somehow meet them, you could talk to them, not just exchange grunts or simple signals, but actually converse, share stories, laugh at jokes, argue about the best way to do something. They would understand irony, metaphor, symbolism. This is what the art tells us, that behavioral modernity, the final flowering of everything that makes us human, was complete by at least 40,000 years ago, maybe much earlier. These weren't proto-humans stumbling toward humanity. These were us, fully formed, thinking the same kinds of thoughts in the same kinds of ways. They looked at a blank cave wall and saw potential. They imagined horses and lions and bears. They mixed earth and charcoal into paint. They made those imagined animals real on stone, and then they walked back out into the light, leaving behind something that would endure for 40,000 years, waiting for their distant descendants to find it and recognize kinship across the vast gulf of time. When we dream in color now, when we create art, when we make music, when we tell stories, we're doing what our ancestors did in those caves. The impulse is the same, the need is the same, the urge to transform the internal world of imagination into external reality that others can share. We learned to dream in color during the Stone Age, and we never stopped. There's a cave in southwestern France called La Chapelle aux Saints. In 1908, two brothers who were also archaeologists discovered something there that would spark a debate lasting over a century. A skeleton, nearly complete, lying in what appeared to be a deliberately dug pit. The bones belonged to a Neanderthal who had lived approximately 50,000 years ago, and the way this individual had been placed in the ground suggested something profound. This might not sound revolutionary. We bury our dead. Every culture does it in some form. But here's what makes this discovery so significant. Burial implies a concept of death that goes beyond mere disposal of bodies. It suggests belief, emotion, perhaps even the first stirrings of what we might call spirituality. It transforms death from a biological event into something meaningful, something that demands ritual response. The Neanderthal at La Chapelle aux Saints wasn't just tossed aside and covered with dirt. The pit had been deliberately excavated into the cave floor. The body was carefully positioned, lying on its side in what almost looks like a sleeping posture. Unlike animal bones found in the same cave, the human remains showed no signs of weathering, no carnivore tooth marks, no scattering by scavengers. Treated with something that looks remarkably like respect. For over a century, skeptics argued about this burial. Were the brothers who discovered it, both Catholic priests, seeing what they wanted to see? Was the pit really deliberate, or just a natural depression? Could scavengers have somehow missed this body while disturbing everything around it? The doubts persisted despite the evidence. Then, between 1999 and 2012, researchers returned to La Chapelle aux Saints. They excavated carefully, documented everything, analyzed the sediments. Their conclusion? Yes, this was definitely an intentional burial. The pit was anthropogenic, created by humans. The rapid covering of the body explained the excellent preservation. The Neanderthals at this site 50,000 years ago were burying their dead. This wasn't an isolated case. At Shanidar Cave in Iraq, archaeologist Ralph Solecki discovered multiple Neanderthal burials in the 1,950 seconds and 60 seconds. One individual, dubbed Shanidar 4, was found with clusters of pollen around the bones. Solecki proposed this was evidence of a flower burial, suggesting Neanderthals had placed flowers on their dead. The romantic idea captured public imagination. Here were these supposedly brutish cave dwellers, and they were laying flowers on graves, just like we do. The flower burial interpretation has been challenged. Pollen can be transported by wind, water, animals. Maybe the pollen got there naturally. Maybe rodents carried flowering plants into the cave. The debate continues. But new excavations at Shanidar, ongoing since 2014, have uncovered additional Neanderthal remains in contexts that strongly suggest deliberate burial. The evidence keeps accumulating. Across Europe and the Middle East, dozens of potential Neanderthal burial sites have been identified. Not all are equally convincing, but the pattern is clear. Neanderthals were doing something deliberate with at least some of their dead, placing them in specific locations, often caves, sometimes positioning the bodies in particular ways, occasionally, possibly, including objects with the deceased. This raises profound questions. What did Neanderthals think about death? Did they have concepts of an afterlife? Did they mourn? Did they perform rituals? We can't know for certain, but we can observe that Neanderthals were cognitively sophisticated. They made complex tools. They used fire. They created art, decorating shells and feathers. They had brain sizes matching or exceeding modern humans. They lived in social groups that required cooperation and communication. It's not unreasonable to think they also had emotional responses to death. Consider what burial requires psychologically. You have to understand that the person is gone. You have to believe that doing something with that body matters, even though the person can't benefit from it. You have to care enough to invest time and effort in ritual when you could be doing other things. Modern humans didn't invent burial. We inherited it. And we share it with at least one other hominin species, Neanderthals, suggesting it might be even older, perhaps emerging in our common ancestor. By 50,000 years ago, when both Neanderthals and modern humans were living in the Middle East, both species were burying their dead. Sometimes in the same caves, separated by thousands of years. The practices weren't identical. Modern human burials more often include grave goods, objects placed with the deceased, ochre pigments, shell beads, tools, animal bones. These inclusions suggest beliefs about death that go beyond simple disposal. What do grave goods mean? They might be offerings to the dead, provisions for a journey to an afterlife. They might mark status, showing that this person was important in life. They might represent personal possessions that belong to the deceased, things too closely associated with them to be used by others. Every interpretation implies symbolic thought, abstract beliefs about death and what it means. The most elaborate Stone Age burials come from the Upper Paleolithic, roughly 40,000 to 12,000 years ago. At Sungir in Russia, archaeologists discovered burials of a man, a boy, and a girl, all lavishly decorated with thousands of ivory beads. The children were buried head to head, surrounded by carved ivory objects including long spears made from straightened mammoth tusks. Creating these grave goods would have required hundreds, maybe thousands of hours of work. Carving ivory beads, sewing them onto clothing, crafting the spears. This represents enormous investment in ritual for the dead. The community valued these individuals enough to sacrifice huge amounts of time and resources on their burials. But not everyone got this treatment. Most Stone Age burials are simpler: a shallow pit, a body, maybe a few objects. The variation suggests that burial practices were differentiated by status, age, circumstance of death, or other factors we can't identify. This social complexity in death reflects social complexity in life. Children's burials are particularly moving. At La Ferracie in France, a 2-year-old Neanderthal child was buried in a deliberately excavated pit. The position of the skeleton, the lack of disturbance, the careful placement, all suggest the child was laid to rest by grieving caregivers. Did Neanderthals feel the same devastating loss that modern humans feel when a child dies? The burial suggests they did. Death also appears in Stone Age art, though rarely. There's a famous scene in Lascaux Cave showing what appears to be a bird-headed human figure near a wounded bison. The human figure is falling or lying down, seemingly dead or dying. This might be a hunting accident, a mythological scene, or something else entirely, but it shows that death was something worth depicting, worth incorporating into the visual narratives our ancestors created. Some researchers think that burial and ritual treatment of the dead might have served practical social functions beyond grief and belief. In competitive environments where different groups vied for territory and resources, burial might have been a way of marking land claims. We buried our ancestors here. This place is ours. The concentration of burials at certain cave sites supports this idea. At Krapina in Croatia, remains of multiple Neanderthal individuals were found, suggesting the site was used repeatedly over time, not just lived in, but returned to specifically for mortuary purposes. This creates continuity, a connection between generations. The living return to where the dead rest, reinforcing claims to territory and identity. But there's something else happening in burial that transcends practical explanation. Burial is a fundamentally irrational act from a purely survival-oriented perspective. Dead bodies pose health risks. They attract scavengers. They can't benefit from burial. The logical thing is to move away and let nature take its course. Yet humans bury their dead. We always have. Even in circumstances where it's difficult, dangerous, costly, we carry bodies great distances to specific burial grounds. We invest resources in grave goods. We return to burial sites to perform ongoing rituals. This behavior only makes sense if death means something beyond the biological. The emergence of burial practices might mark the point when humans developed full awareness of mortality, recognizing your own finite existence. This awareness is psychologically heavy. It demands response, explanation, meaning-making. Every human culture creates narratives about death, afterlife beliefs, reincarnation, ancestor spirits, journeys to other realms. These beliefs vary enormously in details, but they share common functions. They make death less terrifying. They maintain social bonds beyond the grave. They answer the impossible question, what happens to us when we die? We don't know what Stone Age people believed. We can't reconstruct their cosmologies or theologies. But the effort they put into burial, the care they showed the dead, the inclusion of grave goods, all of this suggests they had answers to that question. Maybe not the same answers we give today, but answers that satisfied the need to make death meaningful. There's also the question of grief itself. Did Neanderthals grieve? Did early modern humans? The question seems almost absurd because of course they did. They had complex brains. They lived in tight social groups. They raised children over extended periods. They formed long-term pair bonds. But we can't measure prehistoric grief directly. We can only infer it from behavior. And burial, particularly careful burial with evidence of repeated visits and ritual, suggests emotional responses to loss. You don't bury someone you didn't care about. You don't return to their grave if they meant nothing to you. One Neanderthal burial shows evidence of something remarkable. The individual had severe disabilities, arthritis, missing teeth, injuries that would have required assistance to survive. Yet they lived to old age. Someone, or probably multiple someones, had to care for this person for years, fed them, helped them move, protected them. Then, when they died, buried them. This is compassion. This is empathy, extending beyond immediate reciprocal benefit. This is caring for someone because they're part of your group, because they matter, because leaving them to die alone would be wrong in some fundamental way. The rituals of the dead tell us that by 50,000 years ago, probably much earlier, humans and Neanderthals had crossed a threshold. They weren't just intelligent animals surviving through tool use and cooperation. They were conscious beings grappling with existence, with meaning, with the awful knowledge that everyone they loved would eventually die, and so would they. Burial is hope. Hope that death isn't the end. Hope that the person continues somehow. Hope that the bonds between us persist beyond life's boundary. It's also memory. A physical marker saying this person existed, they mattered, they deserved to be remembered. Every burial from the Stone Age is a message sent across time. Most of the names are lost. Most of the stories are forgotten. But the bones remain. The careful placement remains. The grave goods remain. And they tell us that the people who laid these bodies to rest were people in every sense that matters. They loved. They grieved. They created rituals to manage the incomprehensible. They were us. When you visit a cemetery, when you attend a funeral, when you pause to remember someone who's gone, you're doing what your ancestors did 50,000 years ago in the caves and open grounds of Ice Age, Europe, and the Middle East. But the fundamental impulse, to mark death as significant, to honor the dead, to create meaning in the face of loss, that impulse is ancient. That impulse made us human. Think about the people in your life, not just your immediate family, but everyone. Your friends, your co-workers, your neighbors, the person who makes your coffee, your cousin you haven't seen in years but still care about. How many individuals can you maintain actual relationships with? Not just recognize or know of, but genuinely keep track of their lives. Remember conversations, understand your mutual obligations and history. For most people, the number hovers around 150. This is Dunbar's number, named after British anthropologist Robin Dunbar, who discovered a consistent relationship across primates between brain size and typical group size. Bigger brains can manage more complex social relationships, and humans, with our oversized brains, can maintain about 150 meaningful social connections. This isn't random. This number appears throughout human social organization. Military units from Roman times to the present are most effective when kept around this size. Even modern organizations, when they grow beyond 150 people, tend to fragment into subgroups. But here's the fascinating part. This capacity for complex social relationships didn't emerge recently. It's ancient, baked into our neural architecture over millions of years of evolution. Because for our ancestors, social intelligence wasn't just useful, it was survival. The humans who couldn't navigate social complexity didn't pass on their genes. Being smart about people was as important as being smart about hunting or gathering. Go back 3 million years. Early hominins like Australopithecus lived in groups probably similar to modern chimpanzees. 20 to 30 individuals, small enough that you could know everyone directly, track all the relationships through personal observation. You could see who was allied with whom, who was rising or falling in status, who to trust and who to avoid. But as hominin brains expanded, group sizes grew. By the time of Homo erectus, 2 million years ago, groups were likely larger, 50, maybe 100 individuals. This creates a qualitatively different social environment. You can't directly observe all interactions anymore. You have to rely on information from others. You have to track second-hand knowledge. Alice told you that Bob said that Carol did something to Dave. Can you trust Alice's account? What's her relationship with Bob? Why is she telling you this? This is gossip. And gossip is actually a sophisticated cognitive skill. It requires theory of mind, understanding that other people have thoughts and motivations different from your own. It requires memory for complex social information. It requires language, because you can't gossip effectively without symbolic communication. And it requires the motivation to care about social information even when it doesn't immediately affect you. Anthropologist Robin Dunbar argues that language itself might have evolved primarily for social purposes. In primates, social bonds are maintained through grooming. You groom me, I groom you. We reinforce our relationship through physical contact and time spent together. But grooming is time-consuming and only works one-on-one. You can't groom multiple individuals simultaneously. Language changes this. You can talk to several people at once. You can maintain social bonds through conversation while doing other tasks. You can share social information across the group efficiently. Did you hear what happened? Becomes a way of building coalitions, managing reputations, coordinating group responses to problems. This gossip-heavy view of language origin might seem cynical, but it's actually profound, because effective gossip requires the same cognitive machinery as abstract reasoning, storytelling, and symbolic thought. Once you can gossip about whether Bob is trustworthy, you can also discuss whether rain is coming tomorrow, or tell stories about ancestors, or create myths about gods. The archaeological evidence shows that as brain size increased, social complexity increased too. Tool traditions became more standardized across regions, suggesting cultural learning and transmission between groups. Exchange networks appeared, with raw materials moving hundreds of kilometers from their sources. This implies relationships between distant groups, trusted connections that allowed for trade. By the late Stone Age, 40,000 to 12,000 years ago, these exchange networks were extensive. Shells from the Mediterranean showing up in Central Europe, high-quality flint being transported over mountain ranges. Amber, ivory, ochre, all moving along trade routes that must have involved multiple groups trusting each other enough to exchange valuable materials. This level of cooperation requires sophisticated social institutions. You need norms about fair exchange. You need ways of resolving disputes. You need reputation systems so that groups who cheat get punished and groups who cooperate get rewarded. You need, in short, culture with a capital C, shared rules and expectations that make large-scale cooperation possible. Teaching is another crucial social behavior that demands advanced cognition. Imagine trying to teach someone to make an Acheulean hand axe, those elegant, symmetrical stone tools that dominated the archaeological record for over 1 million years. You can't just demonstrate once and expect them to get it. Making these tools requires understanding the properties of different stones, visualizing the final form, executing a precise sequence of strikes. It takes years to master. This means expert toolmakers had to invest time in teaching novices, had to be patient with mistakes, had to break down complex processes into learnable steps, and novices had to be motivated to learn, to persist through failures, to respect the knowledge of their teachers. Humans are unique in the degree to which we rely on cultural learning. Most of what we know, we didn't figure out ourselves. We learned it from others, who learned it from others going back countless generations. How to make fire, how to track game, which plants are edible, how to read weather signs, how to navigate by stars. All of this is cultural knowledge, stored not in genes but in traditions maintained through teaching and learning. This creates cumulative culture, where each generation builds on what came before. A clever individual might innovate a better hunting technique. If they can teach it to others, and those others teach it to their children, the innovation persists and can be refined further. Over generations, techniques become more sophisticated than any individual could have invented alone. The archaeological record shows this happening. Tool technology generally becomes more complex over time. Early Oldowan tools are simple, maybe 10 or 20 flakes removed from a core. Acheulean hand axes require hundreds of strikes. Late Stone Age tools, microliths, and composite weapons require planning across multiple stages, different materials, combined with precise bindings. This complexity accumulates because each generation teaches the next, adding refinements. But cumulative culture has a dark side. It creates differentiation. Your group does things one way. The neighboring group does things differently. These differences become markers of identity. We make tools like this. We speak like this. We decorate ourselves like this. They do it wrong. We're us. They're them. This in-group, out-group thinking is deeply embedded in human psychology. We're automatically more trusting of people who look like us, talk like us, follow the same customs. We're more suspicious of outsiders, quicker to see threat, slower to cooperate. This served survival purposes when resources were scarce and strangers might be competitors or enemies. But it also enabled larger-scale cooperation within groups. If you trust your group members, you can take risks for them. You can share food knowing they'll reciprocate. You can cooperate on hunts or defense knowing they won't betray you. The flip side is hostility toward outsiders, but within group cooperation was powerful enough to outweigh that cost. Evidence of violence appears in the Stone Age fossil record, though it's relatively rare. Some skeletons show healed fractures from weapons, suggesting interpersonal conflict. A few show unhealed trauma, possibly murder or death in warfare. But the overall pattern suggests Stone Age life wasn't constant violent chaos. Most interactions, even between groups, were probably peaceful or at least neutral. This makes sense from a social brain perspective. Violence is risky and costly. Much better to find ways of coexisting, trading, even cooperating when it serves mutual interests. The sophisticated social intelligence of Stone Age humans would have enabled complex negotiations, peace agreements, intergroup marriages that created alliances. Childcare is another domain where social complexity mattered enormously. Human infants are uniquely helpless. They can't cling to their mothers like other primate infants. They can't walk for a year or more. They require constant care for years and intensive support well into adolescence. No human mother could raise children alone. She needed help. This creates what anthropologists call cooperative breeding. Not just parents, but grandparents, aunts, uncles, older siblings, even unrelated group members all participating in childcare. In modern hunter-gatherer societies, children interact with dozens of caregivers. They're nursed by multiple women. They're carried by various adults. They're taught and entertained by the whole community. This level of cooperative childcare requires trust, reciprocity, and complex social bonds. You care for my child today because I cared for yours last week, because we're both invested in the next generation, because that's what members of this group do for each other. It's social intelligence enabling biological success. Grandmothers are particularly important. Humans are one of the very few species where females live long past reproductive age. Most animals reproduce until they die. But human women typically live decades after menopause. Why? The grandmother hypothesis proposes that older women who no longer have their own young children can invest in their grandchildren, improving their survival rates enough to make post-reproductive longevity evolutionarily advantageous. Grandmothers provide childcare, freeing younger women to have more children closer together. They provide food, especially reliable plant foods that require knowledge to locate and process. They provide teaching, passing down cultural knowledge accumulated over lifetimes. The social brain, then, isn't just about managing relationships. It's about enabling the entire cooperative structure that makes human survival possible. The teaching of skills, the sharing of food, the cooperative childcare, the maintenance of cultural traditions, the navigation of complex group dynamics, all of it requires cognitive capabilities that evolve specifically for social purposes. And here's the feedback loop. As social groups got larger and more complex, brains that could handle that complexity were selected for. Bigger, more sophisticated social brains enabled even larger groups and more complex cooperation. Larger groups created environments where social intelligence mattered even more. Round and round, driving brain expansion and social complexity upward together. By the late Stone Age, humans were living in social environments of stunning complexity, extended networks of related and allied groups, exchange systems spanning hundreds of miles, cultural traditions differentiating one region from another, specialist knowledge holders, individuals who were particularly skilled at tool-making or tracking or healing, social hierarchies based on age, skill, reputation, marriage alliances creating bonds between groups, all of it negotiated through language, maintained through teaching and tradition, enabled by brains that evolved specifically to handle this level of social sophistication. You are a social creature, not as an add-on or optional feature, but fundamentally, at your core. Your brain is wired for relationships. You're driven to understand what others think, to care what they think about you, to maintain bonds and navigate hierarchies and build coalitions. This is ancient architecture, built over millions of years when social intelligence was the difference between survival and extinction. Every time you gossip, you're exercising cognitive capabilities that evolved in the Stone Age. Every time you teach something to someone, you're participating in cumulative cultural transmission that goes back hundreds of thousands of years. Every time you care for a child that isn't biologically yours, you're engaging in cooperative breeding strategies that made human survival possible. The social brain revolution wasn't a single event. It was a long process of brains and societies co-evolving, each driving the other to greater complexity. Not just as individuals with large brains, but as social beings who need each other, who learn from each other, who create cultures that persist across generations. The Stone Age made us smart, but more importantly, it made us social. And that social intelligence, that desperate need to connect and cooperate and belong, that's the most human thing about us. There's a pattern in human evolution that becomes unmistakable once you see it. The same tools, the same lifestyles, the same basic strategies for survival. Then something shifts. Innovation accelerates. New technologies appear. Behaviors change. And within a few thousand years, the world is fundamentally different. The last major acceleration happened during what archaeologists call the Upper Paleolithic, roughly 50,000 to 12,000 years ago. Before this period, stone tool technology had been advancing slowly, glacially, over hundreds of thousands of years. After it began, innovation exploded. New tool types appeared every few thousand years. Bone and antler became common materials for the first time. Composite tools, weapons made from multiple carefully fitted components, became standard. Art flourished. Long-distance trade networks expanded. Population density increased dramatically. Something changed. Not genetically. Humans from 100,000 years ago were biologically identical to us. But behaviorally, culturally, technologically, this period represents a revolution. And that revolution is why humans survived when every other hominin species went extinct. Let's start with tools, because that's what preserves best in the archaeological record. For over 1 million years, from roughly 1.7 million to 300,000 years ago, Acheulean hand axes dominated. These were impressive tools, don't get me wrong. Symmetrical, carefully crafted, effective for butchering and processing. But they were also relatively unchanging. The hand axe you found from 1 million years ago looks basically identical to one from 300,000 years ago. Then things started diversifying. The Middle Stone Age in Africa and the Middle Paleolithic in Europe saw new techniques. Prepared core technology, where you carefully shape a stone core so that when you strike it, predictable flakes detach, already shaped for specific purposes. This requires even more planning than Acheulean toolmaking. You're not just creating one tool, you're creating a tool that will create other tools. But the real explosion happened in the Upper Paleolithic. Blade technology appeared, producing long, thin, incredibly sharp flakes from a single core. From one core, you could get maybe 10 Acheulean hand axes worth of cutting edge. With blade technology, you could get 10 times that much. More efficient use of raw materials, more cutting edge per pound of stone carried. And the blades were just the beginning. They became components in composite tools, a blade inserted into a wooden or bone handle, creating a knife, multiple blades set into slots along a wooden shaft, creating a saw, small blades, microliths, mounted in rows to create harpoon points or arrow tips. If one blade broke, you replaced just that component, not the entire tool. This modular approach to technology represents a cognitive leap. You're not thinking about tools as unitary objects anymore. You're thinking about them as systems, components that can be mixed and matched for different purposes. The same concept that makes modern computers modular and upgradable was being applied to stone tools 40,000 years ago. Bone and antler became serious materials for the first time. Needles for sewing, with eyes for thread. Harpoon points, with barbs that prevent prey from escaping. Spear throwers, atlatls, devices that effectively lengthen your arm and multiply throwing force, letting you hunt large game from safer distances. The bow and arrow probably appeared during this period, though the evidence is indirect because wood and sinew don't preserve well. But we find specialized projectile points that are too small and light to be spear tips but perfect for arrows. This is another force multiplier. A skilled archer can bring down prey from distances where the animal can't even see the threat. Clothing technology advanced dramatically. We know from genetic evidence that body lice, which live in clothing, diverged from head lice around 100,000 years ago, suggesting clothes were being worn regularly by then. But fitted, tailored clothing requiring needles and careful stitching probably emerged later, during the Upper Paleolithic. This matters because clothing isn't just about warmth. It's about expanding your range. With good cold weather gear, humans could survive in environments that would otherwise kill them. They pushed into northern Europe, into Siberia, eventually across the Bering Land Bridge into the Americas. Shelter technology evolved too. The earliest shelters were probably simple windbreaks and caves, but by the Upper Paleolithic, people were building substantial structures. At Mezirik in Ukraine, archaeologists found the remains of dwellings made from mammoth bones. Not just bones used opportunistically, but carefully selected, transported, and arranged into frameworks that were probably covered with hides. These weren't temporary camps. These were engineering projects, homes built to last through brutal Ice Age winters. Fire technology became more sophisticated. Earlier hominins used fire, but Upper Paleolithic people controlled it with precision. They made fire starters, stone and iron pyrites struck together to create sparks. They built elaborate hearths with specific stone arrangements to reflect heat, to vent smoke, to protect flames from wind. They used it to heat-treat stone, making it easier to flake. They used it for hardening wooden spear points. They probably used it for signaling over long distances. All of this innovation required cognitive capabilities we've discussed. Planning, abstract thought, memory, teaching. But it also required something else. The willingness to experiment. The creativity to imagine that things could be done differently. The persistence to try new approaches, even when initial attempts failed. This is where culture becomes crucial. In a purely individual learning system, every innovation dies with its inventor unless they happen to pass it on before death. But in a cultural system with robust teaching and learning, innovations can spread rapidly across a population and persist across generations. One person figures out that heat-treating stone makes it easier to work. They teach others. Those others refine the technique. Within a few generations, it's standard practice across an entire region. The archaeological record shows exactly this pattern. New tool types appear at one site, then spread outward over subsequent centuries, following what must have been social networks and trade routes. Innovation becomes contagious in a way that's only possible with language and cultural transmission. But innovation also creates differentiation. Different groups develop different tool traditions, different artistic styles, different ways of doing things. Archaeologists can identify distinct cultural regions based on artifact styles. The Gravettian culture of Central Europe, the Solutrean of Southwestern Europe, the Magdalenian that followed it, each with characteristic tool types, artistic motifs, settlement patterns. This cultural diversity suggests something important. Humans weren't just surviving during the Upper Paleolithic, they were thriving. Populations were large enough and stable enough to develop regional identities. They had enough resources to support specialists, individuals who focused on becoming exceptionally skilled at specific crafts. They had enough leisure time to create art, music, elaborate rituals, and they were competing, not just with the environment or with prey animals, but with each other. Different human groups encountering each other, sometimes trading, sometimes cooperating, sometimes conflicting. This competition drove further innovation. The group with better weapons has advantages in hunting and in conflict. The group with better clothing can exploit territories others can't reach. The group with more efficient tools can process resources faster. This is where other hominin species started losing. Neanderthals were sophisticated. They had large brains, complex tools, social structures, symbolic thought. In many ways, they were comparable to modern humans. But the archaeological evidence suggests they innovated more slowly. Their tool traditions changed less over time. They seem to have smaller social networks, less long-distance trade, less cultural differentiation. When modern humans and Neanderthals encountered each other in Europe and the Middle East, they coexisted for thousands of years. There was even interbreeding. Most modern humans carry some Neanderthal DNA. But gradually, Neanderthal sites disappear from the archaeological record. By about 40,000 years ago in the Middle East, 30,000 in Europe, they were gone. Modern humans remained. Why? What advantages did modern humans have that proved decisive? The answer is probably multifaceted. Better long-distance weapons, bows and spear throwers, would have made hunting more efficient and warfare less risky. Better, cold-weather clothing would have allowed exploitation of resources during harsh winters. More rapid innovation would have allowed faster adaptation to changing conditions. But perhaps most importantly, modern humans had culture that accumulated and spread faster. Each generation didn't just inherit what the previous generation knew. They added to it. New hunting techniques, new tool designs, new strategies for finding food or avoiding danger. This cumulative cultural evolution created a moving target that Neanderthals, innovating more slowly, couldn't keep pace with. The same pattern probably played out with other hominin species. Homo erectus persisted for over 1 million years, an incredibly successful run, but they disappeared around 100,000 years ago, likely outcompeted by more innovative descendants. Homo floresiensis, the small-bodied hominins found in Indonesia, survived until maybe 50,000 years ago. Then modern humans reached the region, and within a few thousand years, floresiensis was gone. We don't know if these extinctions involved direct conflict, disease transmission, or simple outcompetition for resources. Probably all three played roles at different times and places. But the pattern is clear. As modern humans, with their rapidly evolving cultures spread across the world, every other hominin species vanished. This makes you, reading these words right now, a member of the only surviving hominin species. Every other experiment in becoming human failed. The Neanderthals, with their robust bodies and large brains, the Floresiensis who adapted to island living, the Denisovans who thrived in high altitudes, the Erectus who mastered fire and walked upright across Asia for 1 million years, all gone. But we're here, the descendants of a small African population that figured out how to innovate faster than anyone else. That developed cultures capable of transmitting and building on knowledge generation after generation. That created social networks, allowing exchange of ideas across vast distances. That adapted to every environment, from tropical rainforests to Arctic tundra, through cultural evolution happening faster than biological evolution ever could. The Upper Paleolithic revolution wasn't just about better tools. It was about becoming a species whose primary survival strategy was innovation itself, not adapting to the environment through genetic change, but changing behavior and technology to master any environment. This flexibility, this capacity for endless cultural evolution, this is what made us the survivors. Look around at the world humans have created. Cities, agriculture, writing, mathematics, science, art, all of it is cultural, transmitted through teaching and learning, building on knowledge accumulated over thousands of generations. The roots of all this go back to the Stone Age, to those Upper Paleolithic innovators who figured out that the solution to every problem was to think of something new. We are the innovators. And we survived because we never stopped innovating. So here's the question that's been hiding underneath everything we've explored. When did humans become human? Not anatomically, we can track that through fossils, but behaviorally, cognitively, culturally. When did the modern human mind emerge? When did creatures who looked like us start thinking like us? This question has obsessed anthropologists for generations because the answer keeps changing. Every new discovery pushes the timeline back a little further or complicates the picture in ways that make simple answers impossible. But that complexity is actually the point, because becoming human wasn't a single moment. It was a threshold that our ancestors crossed gradually, unevenly, with false starts and regional variations. The old model was clean and simple. Anatomically, modern humans appeared in Africa around 300,000 years ago. But they didn't act modern. They made Middle Stone Age tools, relatively simple compared to what came later. They lived in small groups, much like earlier hominins. Then, around 50,000 years ago, something happened. The Great Leap Forward. A sudden explosion of behavioral modernity. Art, complex tools, long-distance trade, rapid innovation. This model is appealing because it suggests a clear before and after. It implies that some genetic change, perhaps related to language or symbolic thought, created fully modern cognition in one dramatic step. Find that mutation, and you've found what makes us human. But the evidence doesn't support this simple story. Not anymore. Archaeological discoveries over the last few decades keep finding earlier examples of modern behavior. Shell beads from South Africa dated to 75,000 years ago. Ochre processing toolkits from 100,000 years ago, possible art and symbolic objects from even earlier. Each discovery pushes behavioral modernity further back in time, suggesting it emerged gradually rather than suddenly. Even more problematic for the Great Leap Forward model, we now know that Neanderthals showed many modern behaviors. They buried their dead. They created art, decorating shells and using pigments. They made sophisticated tools. They cared for injured and elderly group members. If Neanderthals were behaviorally modern in these ways, then behavioral modernity can't be the defining feature that separates modern humans from other hominins. So maybe the question is wrong. Maybe instead of asking when humans became human, we should ask what made us different enough to survive when every other hominin species went extinct. What did we have that Neanderthals, Denisovans, Homo erectus, and all the others lacked? The answer seems to be degree rather than kind. Other hominins were innovative. Modern humans were more innovative. Other hominins had social networks. Ours were larger and more complex. Other hominins used symbols. We used them more extensively, more flexibly, more creatively. Think about it as crossing a threshold of complexity. Below the threshold, you can have all the individual components of modern behavior. Tool use, social cooperation, symbolic thought, language. But the components don't quite integrate into a self-reinforcing system. Innovation happens, but slowly. Culture exists, but doesn't accumulate rapidly. Populations remain small and isolated. Cross the threshold, and everything changes. Innovation drives population growth. Larger populations mean more potential innovators. More innovators mean faster cultural evolution. Faster cultural evolution creates advantages that drive further population growth. The feedback loops kick in, and suddenly you're not just surviving, you're expanding, adapting to new environments, outcompeting other species. Modern humans crossed that threshold. Other hominins approached it. Some came very close, but they didn't quite get there. Or if they did, they crossed it in isolated populations that didn't persist long enough to leave extensive archaeological traces. The evidence suggests the crossing happened in Africa, probably between 100,000 and 300,000 years ago, not in a single population at a single time, but gradually, in scattered groups across the continent. Some populations developed certain modern behaviors early. Others were more conservative, sticking to older traditions. Over time, the more innovative populations expanded, their behaviors spread, gene flow connected distant groups. By 100,000 years ago, humans in Africa were doing things that looked unmistakably modern. Creating complex tools, using symbols extensively, building social networks that spanned hundreds of kilometers, adapting rapidly to different environments from coastal regions to highlands to deserts. These weren't proto-humans on the verge of modernity. These were us, behaviorally, if not yet genetically, fully modern. Then, starting around 70,000 years ago, some of these populations began moving out of Africa. Not for the first time, earlier humans had left Africa before. But this time was different. This time they didn't just occupy a few favorable niches and stagnate. They spread everywhere. They adapted to every environment. And they carried their cultures with them, cultures that continued evolving, diversifying, becoming more complex. By 50,000 years ago, modern humans had reached Australia, requiring sophisticated boat building and navigation. By 45,000 years ago, they were in Europe, encountering and eventually replacing Neanderthals. By 30,000 years ago, they'd pushed into Siberia. By 15,000 years ago, they were crossing into the Americas. This expansion wasn't just geographical, it was cognitive and cultural. Coastal foraging strategies don't transfer to high mountains, but modern humans figured it out. Everywhere they went. They didn't adapt biologically to each environment. That would take hundreds of thousands of years. They adapted culturally, in just a few generations. This is the threshold. The point where cultural evolution becomes fast enough and flexible enough to be your primary survival strategy, where instead of waiting for natural selection to shape your body for the environment, you shape your behavior and technology to master the environment, where accumulated cultural knowledge becomes more important than individual intelligence. And here's the profound implication. Once you cross that threshold, you're no longer evolving primarily through genetic change. Your evolution is cultural. The human species hasn't changed biologically in any significant way for at least 50,000 years, probably longer. A person from 50,000 years ago, raised in modern society, would be indistinguishable from anyone else. Same brain, same capacity for language, same potential for abstract thought. They could learn calculus, play piano, understand quantum mechanics. The hardware is identical. But a modern person transported to 50,000 years ago wouldn't know how to survive. You probably couldn't make fire without matches, couldn't find edible plants without grocery stores, couldn't track game or make tools or navigate by stars. All your sophisticated knowledge about science and technology would be useless without the cultural foundation it's built on. This reveals something crucial about human nature. We're not successful as individuals. We're successful as cultural beings embedded in knowledge systems that took thousands of generations to build. Every skill you have, you learned from someone who learned from someone going back in an unbroken chain to the Stone Age. Language, the ultimate cultural tool, exemplifies this perfectly. You didn't invent the language you speak. You learned it from your community, which learned it from previous generations, which evolved it gradually over thousands of years. The grammar, the vocabulary, the subtle rules you follow without thinking, all of it is cultural inheritance. Same with your knowledge about the world. You know the Earth orbits the Sun not because you figured it out through personal observation, but because that knowledge has been culturally transmitted from Copernicus and Galileo through generations of teachers to you. You trust mathematics not because you derived it yourself, but because you learned to trust the cultural system that produces and verifies mathematical knowledge. This cultural dependence is what makes us human in the deepest sense. We are the species that lives primarily in worlds of meaning we create through shared knowledge. Our survival depends not on our individual intelligence, but on our collective wisdom accumulated over countless generations. The Stone Age is when this system crystallized, when cumulative culture became robust enough and fast enough to carry our species through every challenge, when innovation became our defining characteristic, when we stopped being just another hominin species trying to survive and became something unprecedented, a species whose evolution was primarily cultural rather than biological. Every technology you use, every word you speak, every idea you hold, traces back through cultural lineages to origins in the Stone Age. The smartphone in your hand is the descendant of stone tools. The language you speak evolved from vocalizations and gestures developed hundreds of thousands of years ago. The mathematics underlying modern technology descends from Stone Age people counting on their fingers and marking tallies on bones. You are the inheritor of 3 million years of human evolution. Not just biological evolution, though that shaped the brain you're thinking with, but cultural evolution, the accumulated knowledge and skills and stories of thousands of generations of ancestors who survived, who learned, who taught their children, who adapted to impossible challenges, who never stopped trying to understand and reshape their world. They made tools when they were barely more advanced than apes. They learned to walk upright when the forests disappeared. They figured out how to eat meat when plants weren't enough. They grew their brains by changing their diets. They developed language to share their thoughts. They created art to express their dreams. They buried their dead with ceremony and care. They built social networks that spanned continents. They innovated their way through ice ages and droughts and megafauna extinctions. And they survived. When every other hominin species went extinct, modern humans survived. Not because we were stronger, or faster, or better adapted biologically, but because we were more innovative, more social, more cultural, because we learned faster, taught better, accumulated knowledge more effectively. You exist because of choices made by people whose names are lost to time. Because someone 3 million years ago picked up a rock and saw possibility. Because someone 1 million years ago controlled fire and shared it with their group. Because someone 50,000 years ago had an idea and taught it to others who refined it and passed it on. The Stone Age made us human, not through any single innovation or mutation or moment, but through the long, slow accumulation of changes that built, layer upon layer, generation after generation, until something unprecedented emerged. A species that thinks about its own thinking, that creates meaning where none exists, that tells stories about its origins and wonders about its future. You are those Stone Age people, separated by time, connected by culture, carrying forward the project they began when they first imagined that the world could be different and then made it so. The threshold of humanity wasn't something we crossed and left behind. It's something we carry with us, something we recross every time we learn, teach, create, innovate. The Stone Age never really ended, it transformed. The same drives that made your ancestors shape stone into tools now make you shape ideas into understanding. The same social needs that made them gather around fires make you seek connection and belonging. The same creativity that made them paint caves makes you create art and music and literature. 3 million years of evolution, and here you are, conscious, questioning, creating. The universe experiencing itself through eyes, evolved in the Stone Age, thinking thoughts with a brain built by ancient pressures, using language developed by people who never imagined their descendants would speak it to the stars. This is what it means to be human, not a finished state but a threshold continuously crossed, not a destination but a journey that began when the first toolmaker imagined something better and hasn't ended yet. The Stone Age made us human, and we're still becoming,